Today we are going to talk about circles and spheres. Let's start with a circle with radius r. Area of the circle is pi r squared, and if you take the derivative of the area with respect to r, you get 2 pi r. And 2 pi r is the perimeter of the circle. If you consider a sphere with radius r, volume of the sphere is 4/3 pi r cubed, and if you take the derivative with respect to r, you get 4 pi r squared, which is the surface area of the sphere. What is happening here? Let's investigate to see if it happens for other shapes as well. This is a square. If you define the radius similar to the radius of a circle like this, each side of the square is going to be 2r. So the area of the square is going to be 4r squared. And the derivative with respect to r is 8r. And 8r is indeed the perimeter of the square. So it happens like the way it happened for the circle. But what if you define the radius of the square like this? Then each side of the square is going to be r root 2, and the area is going to be 2r squared. In this case, derivative with respect to r is going to be 4r, which is not equal to the perimeter of the square. Now let's look closer. In the first case, if you add to the area a little bit, you have changed the radius as much as delta r, and you have added a small area equal to delta A. And delta A is equal to the perimeter multiplied by delta R, because delta A is just a narrow band with length equal to the perimeter and width equal to delta R. But in the second case, if you do the same thing, delta A is not going to be equal to the perimeter multiplied by delta R, because delta R is not the width of that narrow band you have added. So it means the way this works depends on the way you define the radius or the equivalent of the radius in a case like this. Going back to the circle, it's just like a cross-section of an onion. It's just a bunch of narrow stripes packed together, and if you add one more with thickness dr, you get a change in the area equal to dA. That is a long narrow band with length 2 pi r, which is the perimeter of the circle, and width equal to dr, and of course dA is the perimeter multiplied by dr. For a sphere, adding a little bit to the radius changes the volume by dV, and in this case dV is the surface area multiplied by dr, because this is the volume of just another layer of the onion. So again, derivative of the volume with respect to the radius is going to be the surface area of the sphere. Now consider a balloon and assume that it's losing air through its surface. It's just the surface has tiny holes everywhere, and so it can't keep the air inside of it. So the balloon is going to lose some volume over time. But if you don't want it to lose air, you have to introduce air constantly into the balloon. For example, you can connect it to a pump and add enough air so the volume stays the same. It's easy to see that in any given time, the volume of the air you are adding to the balloon is the same as the volume of the air that escapes through the surface of it. Now, sometimes concepts as simple as this is the center of a very seemingly complex formulas. For example, look at this super scary formula called divergence theorem. It just says the same thing we talked about. The left side is the air going into the balloon, and the right side is the air that escapes through the surface. So a lot of times scary looking formulas are just about simple concepts and you don't have to be scared of it. Now, one thing you might wonder is if we can use this method to find a formula for the perimeter of an ellipse. Because in a circle, if the area is pi r squared, you can take the derivative and get the formula for the perimeter, 2 pi r. And we already have the formula for the area of the ellipse. It's pi a b, and a and b are half of the big and small diameters. Does it mean we can somehow take the derivative and get to the formula for the perimeter of the ellipse? Because as you know, there is no formula for the perimeter of ellipse. But as it turns out, the problem is that if you just add a small constant amount all around the ellipse, is not going to be an ellipse anymore. In fact, in order to have a bigger ellipse, you need to add a little more to the big diameter and a little less than that to the small diameter. It's not going to be a constant increase everywhere. And that is the problem, because the area that you have added to the ellipse is not going to be equal to the perimeter multiplied by some constant increase everywhere. Hope you enjoyed this video. Thanks for watching and check out the channel for more videos like this.